Good afternoon, everyone. So I am going to continue off with the discussion of growth and accumulation. The last video specifically covered the first part of this, which was the introduction to macroeconomic growth and the Cobb-Douglas production function. And in the second part, we're going to extend that discussion. You'll recall in the last video that we were talking about growth accounting theory specifically, and the purpose of growth accounting theory was to try and understand what the contribution is made by different inputs to total output growth. There's also other theories of economic growth that we will look at, growth theories, but those will be covered in future sessions. The reason why it's so important to try and understand how economic growth occurs is because economic growth is really important in order to ensure that over time living standards in countries are improving. And that's what then takes me to the material that we are now going to cover in this video, which specifically is going to be about per capita growth rates. So I'm going to skip through to the slides. Alright, so the last time we were specifically looking at the growth accounting theory equation. And the growth accounting theory equation suggested that total output growth depended on theta, which was the share of capital in total output growth, multiplied by the capital growth rate, plus 1 minus theta, which is the share of labor in total output growth, multiplied by the population or the labor growth rate, plus technological change. Now all of those different growth rates, the output growth rate, the capital stock growth rate, the population growth rate, and technological change, or the rate of growth of technological progress, those are all absolute those are all aggregated levels. They're not per capita levels. Okay, so when we talk about total output growth, we're talking about the total change in GDP, for example. But if we wanted to measure how living standards were changing, we would want to look at the percentage change in GDP per capita. And to account for the growth in GDP per capita, we need to adjust the growth accounting equation. And that's what the next set of materials attempts to do. One of the reasons why we would want to do this, obviously, is because we want to understand not only how economic growth occurs overall, but also to understand the nuances of thinking about economic growth per person. But in addition to that, it's because in some countries they might have relatively high economic growth rates, but if their population is really large, or if their population growth rate is very, very high, then that might affect the amount by which living standards can improve. So for countries that are growing at a very high rate but have a very big population, it might be the case that their living standards don't improve that rapidly, even despite having high economic growth rates. And it's that sort of issue that we want to tackle here. Alright, so per capita income, how do we measure that? Well, per capita income is simply total output, or GDP, divided by the population size. So capital Y divided by N gives us per capita income, or per capita output. So output per person refers to the total amount of output in the economy divided by the population size. If the population in an economy was 1,000, and if output in the economy was 10,000, then 10,000 divided by 1,000 would give you the output per person. Rearranging that, total output is equal to output per person multiplied by the total population size. And what we can then see, and it's this that I'm going to work through with you, is that the growth rate in total output is actually equal to the per person output growth rate plus the population growth rate. And it's this that I want to just tease out a little bit, because it's not obvious, well, at least it's not immediately obvious how that is obtained. So I'm going to switch to the pay-per-view. Let's move those out the way. Alright, so output per person is equal to total output divided by the population size. Okay, just as an example so that you know what's going on. If total output was, say, 1,000 and the population size was 100, then output per person would be 10. Okay, really quite simple. Total output is then equal to output per person multiplied by the population size. If we then look at the change in total output, that's going to be equal to the change in output per person multiplied by the population size plus the change in the population size multiplied by output per person. If we then divide through, so here we're going to divide through by y, then what we have is the growth rate in output is equal to 1 over y multiplied by change in y multiplied by n plus 1 over y multiplied by the change in the population size multiplied by output per person. Okay, what we now do is we exploit that formula there. So I'll show you how that works now. Okay, we know that overall total output is equal to output per person multiplied by the population size. So here we can substitute in little y n, and that's then change in y and multiplied by n, plus over here we do the same thing, so that's little y n, change in n and y. And what you now see is that these things cancel out, and that makes life very nice. So that cancels out with that, and that cancels out with that, and what you are left with is total output growth. So this is the change in big Y over big Y, is equal to the change in little y over y plus the change in n over n, where this is total output growth, this is, and that's equal to the growth in output per person plus population growth. Okay, so what we've done is we've transformed what is simply a relationship between total output and the population size and working out output per person. We've transformed that to be able to understand how the growth rate in total output relates to the growth in output per person and the population growth rate. Alright, now that we have gone through that, let's move back to the slides. Current slide. Okay. So that's essentially what I have gone through, but I did it on the screen. And what it shows is that the growth of total output, over here, the growth of total output is accounted for or is explained by the growth in per capita output as well as the population size growth taken together. Okay. Alright, if we were to now rearrange that equation and make the growth rate and output per person the subject, in other words, what we've done is we've put in here on the left-hand side, what we're interested in is the growth rate and output per person. That then becomes equal to total output growth less the growth in the population. So to translate the growth accounting equation into per capita terms, we subtract population growth. Similarly, if we wanted to get to the capital to labor ratio, where the capital to labor ratio, small k, is equal to total capital divided by the population size, then the growth in the capital to labor ratio would be equal to the growth in capital stock less the growth in the population. And I'm not going to go through this one because I think that that's a useful exercise for you to try and solve that for yourselves. Okay. Alright. What we now want to do is delve a little bit deeper, because what we know is that per capita output growth depends on the growth in total output less the population growth. But we also know that the growth in total output depends on the capital growth rate, and it depends on the share of capital in total output growth. So what we want to do is have an expression for the per capita output growth rate that gives us a little bit more detail than simply suggesting that you can take the output growth rate and from it subtract the population growth rate, because this equation as it stands doesn't tell us anything about how changes in capital stock per person, for example, will affect the growth rates in output per capita. And so what we need to do from this equation is, if we subtract the population growth from both sides of the growth accounting equation, so if you look here on the left-hand side, our growth accounting equation is change in y over y is equal to theta, change in k over k, plus 1 minus theta, change in n over n, plus change in a over a. What we've done in this line, in this equation, is we've simply subtracted the population growth rate from each side of that original growth accounting equation. What we then do is, over here you'll notice that what we have as the expression on the left-hand side is the total output growth rate less the growth in the population. And now we know that the total output growth less the growth in the population is simply the per capita output growth rate. So that then allows us, in the second line of the equation, to substitute this expression with its answer, which is the per capita output growth rate. Okay? What we can then see is, when we simplify the expression on the right-hand side, it works out to theta multiplied by the growth in capital stock plus the population growth rate into 1 minus theta minus 1, okay, plus the change in technology. Simplifying further, we have the per capita output growth rate is equal to theta multiplied by the growth in capital stock less the population growth rate plus the change in technology. And similarly to before, we had learned that taking the total capital stock growth less the growth in the population size, the answer to this expression is simply the growth in output per person. So we can substitute that in here. And what we then can see is that in per capita terms, the growth in per capita output depends on the share of capital in total output growth, as well as the per capita output growth rate and technological change. What we should then note is that the number of machines per worker, K, is a really key determinant of output produced by a worker. But since theta is less than 1, if capital per worker increases by 1%, that would result in a less than 1% increase in output per worker. So to see that, and I will flip to the pen view shortly, just writing down the equation. Okay, so I just get out of this and go here. Alright, this is now our equation, our growth accounting equation, but for per capita output growth. And what we can see is, if we say that there's no technological change, okay, so if we take that part of the equation out, let's say that theta is equal to 0.3, and let's say that the growth rate in per capita capital stock is equal to 1%. Then what that's telling us is that total per capita output growth is going to be equal to 0.3 multiplied by 1. And that is simply 0.3. So what we see is that because the share of capital in total output growth is typically quite low, around 0.25 or 0.3 in many cases, the contribution, or the overall contribution of changes in capital stock per person to changes in the growth in output per person is still quite low. So if capital stock per person was to increase by 1%, overall there would be a less than 1% increase in output per person. Here, capital stock per person grew by 1%. Because theta was 0.3, output per person only grew by 0.3%. even if capital stock per person was to grow by, say, 5%, and theta was 0.3, whoopsie, changing y over y, capital per person could grow by as much as 5%, but because theta, the share of capital in capital stock and output growth, is quite small, overall, the growth in capital stock per person only contributes, or would only affect output per person growth by 1.5%. All right. Let's go back to the slides. Okay. So what can we therefore conclude about overall growth accounting theory, specifically the growth in total output versus the growth in output per person? The first conclusion is that in terms of overall GDP growth or overall output growth, change in capital Y over Y, the important determinants of overall GDP growth are technological progress, increased labor supply, as well as capital accumulation. And those three things are all key components of the overall growth accounting equation. In terms of the growth in per capita output, the important determinants of the growth in per capita output, or GDP per person, change in little y over y, are technological progress and capital accumulation. There, the components of the equation are change in A over A and change in little k over little k. Alright, to move along, we now need to think about how some of these things could be useful. And so we think about what's called some of the convergences that may have happened in countries over time. What the table in the slide is trying to show us is a comparison of growth rates between, in GDP per capita and in capital stock per capita, between two countries, specifically the United States and Japan. So what we've got is what's called post-war annual growth rates. Post-war because the estimates are starting from the 1950s. On the left-hand side, we've got growth rates in GDP per capita. So for example, the 1950 to 1973 figure of 2.42 for the United States is saying that GDP per capita growth for the United States over that period was 2.42%. GDP per capita growth for Japan over that period was 8.01%, and the difference in GDP per capita growth between the two countries over that period was 5.59%. On the right-hand side of this table, the figures are showing the growth in capital stock per capita. So this is change in little k over k. And what we can also see then is how much capital stock per person was growing in the United States relative to the growth in capital stock per person in Japan. And what you should notice is that, across all of these years, Japan was investing quite heavily in capital stock per person. So their rates of growth in capital stock per person were exceeding the rates of growth in capital stock per person in the United States. And then, if you look on the left-hand side, the growth rates in GDP per capita were also exceeding the growth rates in GDP per capita in the United States. So I'll show you a little bit how we can use these figures in a second, but just at face value, what the table seems to suggest is that capital accumulation, although it might not be the only determinant of growth, it can be a very important determinant of growth. And furthermore, that perhaps we should start thinking about, and this is where we start thinking about growth theory more generally, what countries can do in order to be able to increase or improve their capital stock. What I want to do, though, before we start thinking about that, is just to show you how some of these figures can be used with the per capita growth accounting equation that we've just been talking about. So I'm going to shift again to the writing view. Okay, so working with 1950, to 1973 for the US. Okay? If we wanted to use the figures that were in that table to work out how much technology contributed to the growth in total output per person, remember that our equation for the growth in total output per person is equal to theta, change in little k over k, plus change in A over A. So if we wanted to know what the contribution of technology was to changes in capital stock per person, we could simply rearrange the equation if we had the other data. So what we know from the table is that the total amount of GDP per capita growth in the US from 1950 to 1973 was 2.42%. From that, using this equation, we can subtract, if we assume theta is, say, 0.25 multiplied by 1.78. This 1.78 is also taken from the US figures from 1950 to 1973. And in that table, we saw that the amount of capital stock per person in the US grew at a rate of 1.78%. Okay? So what we can then see is that we take 2.42 minus, this works out to 1.53, and we get an answer of 0.89. Okay? So over the period in the US when output per capita grew by 2.42%, 1.53% of that 2.42% growth was accounted for by changes in capital stock per person and the share of capital in total output growth. The remainder of the output per person growth that took place can be explained by technological improvements, and specifically the technological improvements accounted for about 0.89% of the total output growth. We could do the similar thing for Japan. So again, 1950 to 1973, this is now Japan. Change in A over A is equal to change in Y over Y minus theta, change in K over K. So the figures for Japan, recall they were quite a bit bigger, 8.01 minus 0.25 and 7.95. Okay? So we're assuming theta is 0.25. Output per person growth is 8.01, that's from the table. 7.95 is the growth in capital stock per person. Again, that was also from the table. We then go 8.01 minus 1.9875. That figure is what happens when you multiply theta by the per capita growth rate in capital stock. And what that works out to is 6.0225. Alright, what I'd like you to do is simply just compare those figures. Okay? Over the 1950 to the 1973 period, what we can clearly see is that not only in the US were they investing less in capital stock per person, okay, the US was investing only 1.78% in capital stock per person, whereas in Japan, the growth in capital stock per person was 7.95. But in addition to that, the technological change accounted much more for the growth in output per person that took place in Japan as compared to in the US. So in the US, technological change was not as rapid as it was in Japan. The final thing that I want to show you is how you can use these figures to deal with the difference between Japan and the US. So difference between Japan and the US, and again, change in technology is equal to change in Y over Y minus theta, change in K over K. So these differences are taken from the table where the column was showing difference. And again, I'm working with the 1950 to the 1973 period. The difference in output per person between Japan and the US in 1950 to 1973 was 5.59. That's from the table. Okay. 0.25 is the value we're assuming for theta, and the difference in capital stock per person was 6.17. If we then work with the figures, minus 1.5425 is equal to 4.0475. Okay. So what this is suggesting is that of the difference in output growth that took place between Japan and the US, that difference was accounted for mostly by differences in technological change, and specifically differences in the rates of technological change between the two countries accounted for 4.0475 of the difference in output growth per person between the two countries. Okay. All right, let's move back to the slides. Okay. All right, so now we understand a little bit about what contributes to economic growth. What has the research shown? Well, Solo, who has been one of the main researchers who have attempted to investigate what has been causing economic growth, and specifically what the factors are that have accounted for most of the growth which has taken place, particularly in the US, because that's one of the biggest economies in the world. Robert Solo found that over 80% of the growth in output per labor hour in the US was due to technical progress. And that seems to make sense also if you look at or consider the figures which we've just been looking at. It really seems to be technological progress that has driven much of the expansion in economic growth over the recent period. And that's because it's very difficult for countries to access additional resources, additional land and additional capital. What's really made a large contribution to changes in economic growth has been technological advancements, such as the Industrial Revolution being one of them, but also the computer revolution, for example. The important determinants of GDP growth that have been found in the literature really are technical progress and capital growth. It's actually been found that increasing population sizes decreases GDP per capita, although increasing GDP. Why would this be? Well, it's because of diminishing marginal returns. Think about how GDP per capita is calculated. If you have more labor, you can clearly produce more output, but output will increase at a decreasing rate. In addition, if you then have to take that total output, which is increasing at a decreasing rate, and divide it by a population size, which is getting bigger and bigger and bigger as the population grows, you will see that eventually GDP per person might decline. So economies that have had really high population growth rates have really struggled to improve their living standards, even if total levels of GDP have been increasing over time. And that's something which we will definitely come back to in future sessions. The research has also suggested that other than population size and capital, there are other factors that are really important to consider in terms of thinking about what can affect economic growth. Obviously, the most important one would be human capital, the actual quality of the labor force which is being used in countries around the world. And this is why investments in human capital, often shown by a capital H, through schooling, on-the-job training, and even health expenditure, those have all been considered and realized to be very important determinants of output in many economies. If you think about countries like South Africa, where the HIV and AIDS pandemic has really wreaked havoc, particularly in the 80s and in the late 70s, and the fact that during the 90s we were trying to play catch-up in terms of preventing the virus, that really did have a very severe effect on the population in the economy. The health of the population is really important, because if workers are unable to go to work because they are sick, that can negatively affect output. If individuals are unable to obtain jobs because they are unwell, that again can also negatively affect output. So health considerations, as well as the quality of the labor force in terms of the skills that that labor force has, are critical in determining how much output can be produced with the existing quantity of labor that an economy has available to it. So adding human capital, for instance, into the production function, we can write the general form of the production function as follows. Total output is equal to the technological change, and that's a function and is also a function of capital stock, human capital, and the population size. Researchers Mankey, Roma, and Veal suggest that the contributions of human capital, physical capital, and the population size are roughly all equal to economic growth. So each of those factors contributes approximately 1/3 to economic growth. According to Dornbush, Fisher, and Stotts, approximately 80% of the variations in GDP per capita between countries can actually be explained by differences in the growth rates of physical capital, human capital, and population size between the countries. If we think specifically about factors other than the population size and physical capital and consider human capital, it's really interesting to think about what's going on if we look at the figures on the right-hand side of your screen here. The first diagram is showing the investment ratio relative to per capita GDP. Okay? So what it's suggesting here is that countries that invest more have a higher level of per capita output. So Ghana, remember Ghana was one of the countries that we spoke about in the previous video, and Ghana had a very low per capita output. And Ghana's per capita output is really low, and its investment ratio is very low. Bangladesh, although we didn't consider Bangladesh's figures specifically, GDP per capita in Bangladesh is very low, and it tends to invest very little. So investment in capital stock is very low in Ghana and in Bangladesh. In countries where investment in capital stock is higher, such as Taiwan, Hong Kong, the US, Norway, and Japan, those were the 3 countries that we were looking at in the previous video, those countries where investment in capital stock is higher typically have higher levels of GDP per capita. So what we need to start asking ourselves is, well, why do countries like Ghana and Bangladesh not invest more in capital stock if there is this positive relationship between capital stock and total output per person? The second figure gives us another very glaring idea as to what could be going on in terms of GDP per person in the developing countries versus the developed countries. On the horizontal axis, what we're measuring here is average years of schooling. So this would be a very crude measure of the quality of human capital, the fact that some people may have achieved higher levels of education just in terms of the years that they have been at school relative to others. Ghana and Bangladesh, the average years of schooling that are being shown here are less than 4 years of schooling on average in the population for Ghana, and less than 3 years of schooling on average in the population for Bangladesh. They have very low levels of output per person. As the amount of schooling on average that the population achieves increases, that tends to be associated with an increase in GDP per person. So this suggests that human capital, even when it's measured very crudely in terms of the number of years of schooling on average that the population has achieved, is very highly correlated with living standards. Countries that have a population which are better educated typically have levels of GDP per person which are much higher. Again, this begs the question, why is it the case that in these developing countries more is not being done, or what isn't being done to ensure that the levels of schooling amongst the population improve? Because it is only through improving the levels of investment in capital stock and improving the levels of schooling that levels of GDP per person and living standards can improve. Okay. We've now reached the end of what would be session 2 of the course, and just to recap very quickly, the point of these sessions has been to consider what's going on with economic growth. Why is economic growth important? It's important because it allows us to see how much output is changing in a country, and also because changes in economic growth filter through and affect a country's living standards. We spoke about growth accounting theory and used growth accounting theory to show that inputs, specifically capital and labor, are really critical to determine how much output grows by. In addition, we also considered the fact that technological change is really important to consider by how much output grows. We then went one step further and considered growth rates in output per person, and we transformed the growth accounting equation to a per person growth rate equation, where we looked at the growth in output per person as being a function of the share of capital in total output growth, the growth rate in capital stock per person, and technological change. We then spoke briefly about the real-world data, and we were comparing the US and Japan, and we showed that in the US and Japan, Japan appeared to have been doing much better than the US, not only because they have invested more in capital stock per person, but also because the technological improvements that took place in Japan were far quicker, or there was far more technological progress in Japan than in the US. And then finally, we have just spoken about some factors other than capital and labor, which can affect the amount of output growth and ultimately living standards. And one of the obviously very important ones to consider is human capital, both in terms of the level of schooling that people in an economy have achieved, as well as the health levels of people in the economy. Essentially, improving human capital can go a long way to also ensuring that living standards in economies can improve. In the next set of videos that we do, we will be looking to start understanding something called the neoclassical growth theory. And the neoclassical growth theory starts to answer the question of what can countries do to improve their levels of capital stock per person. Because as you know, the growth accounting theory only allowed us to show that we need more inputs to get more outputs. The neoclassical growth theory is going to go some way to try and explain how we can go about getting more inputs in order to increase our outputs.